Okay, looking more closely to Quicksort in this video, we are going to see how it will be implemented in C++. A quick reminder, the idea of Quicksort is based on divide and conquer. We choose an element of the input array called x, and then we partition the array into two segments. Everything that is less than x goes to the left, everything that is greater than x goes to the right, and then x in the middle. One of these can include x in case that the repetition is allowed. So we have multiple occurrences of x. They can go to the second or the first segment. It doesn't make a difference. But then when we do the partitioning, we call quicksort recursively on both segments to get everything that is less than x sorted and everything that is greater than x also sorted. And then x is obviously in the middle. And the combination part, when you combine the result of your recursive calls to get the final result, is trivial because if you just put these together, the result is going to be sorted. So this is quicksort. And if you want to implement this, as I said, most of the work will be the first step, the partitioning, and we are going to define a separate function only for partitioning. But if we have that, then quicksort itself is going to be very simple. So if I want to use templates um, so that this quicksort function is generic, then I can say template type name T, and then the signature of quicksort will be it's a void function called quicksort, and then the arguments are an array of type T. And similar to merge sort, I need to know from which index to which index this sorting is happening. So int begin and int end. So from index begin to index end, we are going to do this process. And this is because we don't want to really create arrays. We want to do everything in place. So instead of creating new arrays, we just change these two indices to take care of the recursive calls. Okay, now the first step is partitioning. So assuming that I have a partition function, I call my partition function. So I call partition on A and begin and end. And I fixed the way, I'm assuming that I fixed the way on choosing the pivot. Either I always choose the first element or the last element, or randomly pick one of the elements in the input array as my pivot, and then begin and end and A are determined. So partition does this. So it rearranges the elements in the input array so that everything is less than x is before, everything that is greater than x is after. And first, of course, it picks x. Let's say the last element as the pivot. And then I'm going to implement this function so that it returns the index of the pivot. So it returns an integer that tells me where the pivot is located. So what I do is I call partition and then I store its return value in an integer variable called p. So p is the position of the pivot. Okay. Then I call my function recursively. So quicksort on the same array, and the indices for the first recursive call is on the left segment. So it starts at begin, but ends at this index is p, so right before that, right? P minus 1. So that will be the left segment. So begin is here, end is here, and p is the index that the pivot is stored at. Okay, so that's my first recursive call, and then the other recursive call, quicksort on the right segment. It starts from here, so this is p minus 1, and here the first index is p plus 1, right? It's the same array, but it starts at p plus 1 and ends at And that's basically it. That's your quicksort. The rest of it is going to be implementing the partition function, which requires a little bit more work. So let's see how that is done. So again, template, type name T, make it generic. It's going to be a function that returns an integer, which is the position of the pivot, right? And the name was partition. And the parameters are the array of type T, call that A, and the two indices begin and end. Okay. Now, there will be an index called I, which is the index before begin, so begin minus 1. And as I said, for pivot, there are different ways that you can choose the pivot, but in this lecture, I'm using the last element as the pivot. Okay, so A at n, the last element in the array that we are partitioning will be my pivot. And then I need another index j, which is begin. So the first element in the segment that we are partitioning, the index of that first element. Okay, now this j is going to start from begin and go all the way to n minus 1. So for j less than or equal to n minus 1. So it goes all the way to the end almost, but it doesn't go to the last element. Because the last element is the pivot, j plus plus. So one at a time, starting from the begin plus 1, begin plus 2, all the way to n minus 1. So it doesn't cover n because that's where the pivot is selected, right? So it says if a at index j is less than the pivot, then increase I and swap a at I with a at j. And after the for loop, what we do is we do another swap after the for loop, sorry. Swap a at I plus 1 with the last element, which is the pivot. So this last swap moves the pivot to where it actually is supposed to be. Okay, and now we're completely done with rearranging all the elements. The only thing left to do is to return the index of the new index of the pivot, which is I plus 1. Remember, it was at index n. Now it moved to index I plus 1. So there you have it. Okay, and now the way that these indices and swaps work can be confusing. So I'm going to do an example here where I go through this code for partition step by step. Okay, so let's assume that my array partitioning looks like this. So we have 10, 7, 11, 4, 16, 21, 8, and 9. Okay, so this is the array that I am partitioning. So begin is this index here, and end is this index here, right? And note that begin and end are not necessarily, begin is not necessarily 0 because this could be somewhere in the middle of the recursive calls. So the original array could be larger than this, and then in one of the recursive calls, begin happens to be here. So this is not necessarily the entire array. Okay, so if you look at the code that is written here, we have two more indices. We have I, which is the one before the begin, so I is here, one index before, and J is exactly starting at begin, so J is here. Okay, now, and pivot is obviously this guy, so pivot is 9, the last element, right? A and N. Now, if you take a look at this code here, J is going to go from where it is, which is begin, to begin plus 1, begin plus 2, begin plus 3, and so on. So in the first iteration, J is equal to begin. J is equal to begin. And then what we do is we have a condition here. It says compare A at J with the pivot. So A at J with the pivot. So A at J is 10, pivot is 9. It says if A at J is less than the pivot, which it isn't, do something, right? Increase I and swap AI and AJ. But it's not in this case. So what we do nothing, right? And I forgot, did I forget to close the bracket for the for loop? Yes, I did. Okay. So if a statement ends, let's say here, and then the for loop ends here. Yeah, this is one last swap after the for loop. Okay, better. So nothing happens because the condition of the if statement was not true. So we go back and J increases to begin plus 1. So second iteration, J is equal to begin plus 1. Okay, so now J is here. And what do? We compare AJ with the pivot. If AJ is less than pivot, then we have to do something. In this case, it is. So what do we need to do? It says, first of all, increment I plus plus. So I goes here, right? Look at the code. The first thing that you do is I plus plus, and then you swap AI and AJ. So 10 and 7. Let's see if I can erase it without erasing it. Okay, not bad. So it was 10 and 7, now it becomes 7 and 10. And that's it. That's all we need to do. Now, in the next iteration, when J is begin plus 2, in other words, J is here. Remember, J is going to go all the way to the end, right? And in a moment, I explain what's happening with I and J, what is the meaning of these two indices. But for now, let's do one more iteration, and then I will be able to tell you what do these two indices represent. Okay, so J is here now, begin plus 2. Again, we compare A at J with pivot, and if it is less than, then we have to do something, but it's not. A at J is not less than the pivot, so again, we do that. Okay, next iteration, J is begin plus 3, so J is here. Okay, now is A at J less than the pivot? Yes, it is. So what do we need to do? We need to increment I, so I goes to the next index here. And then we need to swap AI and AJ. Now, here's a good place to start thinking about what's going on with this AI and AJ. So whenever we see something that is less than the pivot, we swap it with AI, which means that we move it to the left side. Okay, and that's how we partition. Now, before doing the I plus plus, I is always before the first element that is greater than the pivot. Okay, so I was here, right? Before 10, which is less than, greater than the pivot. 10 is the first element that is greater than the pivot, and I was the index right before that. So that's the story of I and J. It becomes more clear in a moment. Okay, so increment I, so I is here, and then swap A, I, and J. So 10 and 4. So 4, 10. Okay, then next iteration, J becomes begin plus 4. So J goes to the next location. Okay, is A at J less than the pivot? It's not, so do nothing and go to the next iteration. J becomes begin plus 5. It goes here. Is A at J less than the pivot? No, it's not, so do nothing. J goes to the next index, begin plus 6. So here, is A at J less than the pivot? Yes, it is. So it should be moved to the left side. Okay, now look at I. Where is I? I is right before the first element that is greater than the pivot, isn't it? 7 is less than the pivot, 4 is less than the pivot, but 11 is the first element that is less than the pivot. And I is the index right before that. So when I do I plus plus, look at here, if A is less than the pivot, move I forward. So when I do that, I will be the index of the first element that is greater than the pivot. And what do we do now? We swap AI with AJ. AJ was an element that was less than the pivot, and AI is the first element that is greater than the pivot, so we swap these two. So 11 and 9. So 9 goes here, and 11 goes here. Okay, so now you see that 7, 4, 9 are all less than the pivot. I'm sorry, not 9, 8. Like that. J is here, right? So 8 goes here, 11 goes here, and 9 doesn't move at all, right? Because AJ is here. Okay. Um, so now you see that 7, 4, and 8 are all the numbers that are less than the pivot, and they are gathered all on the left side. Okay. And we are done with the loop because J is at n minus 1, and that's the upper limit of the loop. So we get out of the loop, and there's only one more thing, or actually two more things left to do. First of all, we need to move the pivot, which is at the end. It was at the end from the beginning. We never moved it. Move it to the right place. Now, where is the right place for 9? Right after this last element, which is at index I. That's why we are swapping A at I plus 1 with A at n. So A at I plus 1 is this guy, and A at n is this guy. So 9 and 10 will be swapped. And that's the last swap that we do. So 9 goes here, and 10 goes here. And remember that 9 was our pivot. I'm going to draw a circle here to emphasize that. And now you see that this is the pivot. Everything before it is smaller than the pivot, and everything after that is greater than the pivot. Not necessarily sorted. That's not a guarantee. Sometimes, very rarely, but sometimes you may get lucky and these are sorted, but they're not at this moment, right? And that's why you need to call Quicksort recursively on this part and this part. But everything before the pivot is greater than, I'm sorry, less than the pivot, and everything after is greater than the pivot. So partitioning is done. The only thing left is to return the index of the pivot. and I is here, so the index of the pivot is I plus 1, and that's why we return I plus 1 at the end. So hopefully this example illustrates, what's going on with these two indices, excuse me, and the way that they work together. But there you have it. So this is your partition function. This is exactly C++ code. You can type it in and run it. And this is the quicksort itself. And if you have an array, say, of size 10, then you have to call quicksort where begin is 0 and end is 9, the last index, right? So whatever the name of your array is with 0 and 9, or 0 and size minus 1 in general. And then it calls the partition, and the partition does the partitioning, chooses the pivot, does the partitioning, returns the index of the pivot, and then you recursively call quicksort on the first segment and the second segment using the index of the pivot returned by the partition. So that's all there is to it. Now, in terms of the time complexity, similar to merge sort, because this is a recursive function, analyzing its running time requires a little bit of mathematics that I don't want to go to in this series. Later on in an algorithm series, I will work on these extensively. But for now, let's just say that for quicksort, for the worst case, the running time is quadratic, order n squared. So in that sense, it's worse than merge sort, because for merge sort, the worst case was order log n. But average case, which means on a normal input, not some strangely arranged input. So if the positioning of the elements are random or normal or something like that, then the runtime is order n log n. Okay, now in theory, this may seem worse than merge sort, because for merge sort, both of these are n log n. Worst case is n log n. Here, worst case is n squared, so it means that once in a while it's going to be slow. But the thing is, first of all, these worst cases don't happen very frequently, and also it's true that both merge sort and quicksort have order n log n on average, but the constant coefficients are much nicer for quicksort. And as a result, quicksort works very well in practice, actually better than merge sort. So in theory, because of order n squared, some may say that it's worse than merge sort, but in practice, it works very well. It works well in